Momentum is known as the quantity of motion that an object has. No matter how large the object, if the object is not moving, it has zero momentum. This is why momentum is often called mass in motion. Right now, the soccer ball has zero momentum. However, when I kick it, the ball now has momentum.
That's pretty good.
11, 12.
Ping pong balls are great for ping pong, but they're not for bowling. Not enough momentum.
Oh, a scientist.
Bowling balls are about 3 kilograms. They're heavy enough, and we can get them moving fast enough so that they have enough momentum to knock down all the pins at once. That is, if we can hit it just right. Well, that was pretty good. But suppose we had a heavier ball, like 4 or 5 kilograms. Then it would have enough momentum to knock down every pin every time. Now, that would be cool.
Hey, Bill.
Huh?
Catch.
Oh.
The formula for momentum is P equals mv. To calculate the momentum of the ball, we use the mass and the velocity. The average mass of a soccer ball is about 1.5 pounds, and the average speed of a soccer ball is about 60 miles per hour. By using the formula, I plug in the mass, which is 1.5, and the velocity, which is 60, and multiply them both to find the momentum, which is 90 newtons seconds. When referring to momentum, there are two types of collisions. There are elastic and inelastic collisions. In an elastic collision, all the energy and momentum is conserved. This only happens on the atomic level. With solid objects, some of the energy is lost due to the collision and friction. A close example of an elastic collision is Newton's cradle.
You have a virtual Newton's cradle right here. And so what I can do is I can lift up on this ball on this side. Oh, there's a slight pause there. But what happens is the balls on the other side are going to move up. And so what's happening to the momentum is just moving back and forth and back and forth. Now to get one of these work, it actually is pretty hard. You have to make sure that all the balls have the exact same mass, and you have to make sure that they're all the same height. Let me try to grab that for a second. Ooh. So next thing I could do is lift up 2. And so if I have 2 balls now, I've doubled my mass. It's going to have the same velocity, so when I let it down, that momentum is going to be transferred back and forth again. So that's cool. The one thing you want to play with as you do this is then what happens with 3. So if I lift 3 up like this, let me get those stopped for a second. There we go. Okay. If I lift 3 up on this side, what's going to happen there? Well, the momentum's going to be the same. And so how am I going to get 3 balls to go up on the other side? Well, let's just try it. So what happens is 2 will maintain their position, and then that momentum is transferred back and forth. And so momentum, remember, is conserved in any kind of a collision.
To calculate the momentum of an elastic collision, we use the formula m1v1 initial plus m2v2 initial equals m1v1 plus m2v2. For the Newton's cradle example, the momentum of 2 balls is 4 newtons because the mass of 2 balls is 2, and the velocity is 2 meters per second. The momentum of the other balls is 0 because they are at rest. After the collision, the momentum of the first 2 balls is 0 because they are at rest, and the momentum of the other 2 balls that have been set in motion is 4 because the mass of the 2 balls is 2 and the velocity is 2, showing that the momentum has been conserved after the collision. The other types of collisions are inelastic collisions. An elastic collision is when momentum is conserved but some of the energy is lost. Most real-life collisions are inelastic collisions. An example of an inelastic collision is when 2 objects collide. To calculate the momentum of an inelastic collision, we use the formula m1v1 initial plus m2v2 initial is equal to m1 plus m2 times v. The first hockey player weighs 100 kilograms and is moving at 10 meters per second, and the second hockey player making contact weighs 100 kilograms and is moving at 15 meters per second. When they collide, their combined mass is 200 and they are moving at 12.5 meters per second. Both equal 2,500 Newton seconds. This shows that the momentum is conserved after the collision.